the first section is already captured here. 2 hours and 9 minutes. So now we start the next session. I hope you can hear me. Otherwise, please let me know. Let me check the device volume. Hello. Yeah, I think the microphone is okay. All right. Let's get back to our next lab here. So for the following 2 labs, we're going to use the online simulation called the multi-sim. Okay, I'm not sure whether you're already signed up with the multi-sim website or not. Let me show you how to sign up. Okay, you type multisim.com. Okay, I think you can sign up for this so-called multi-sim live. Click here to sign up. Okay, just give them your email address. I think it's really quick. You can sign up the one account. I'm going to log in with my existing account. With this account, you can save your circuit actually. All right, let's start a new circuit. Okay, I give you some time for you to prepare to sign up for this multi-sim. I think you need 5 minutes is good enough to sign one account. So what is the next lab about? Let's see. Lab number 4, question number 6. Let's copy these two into the start with the new page. Start on the new page. Question 6. Lab 4 is about DC motor. So we're going to simulate DC motor using the online simulation tools called multi-sim. Okay, basically this is a model of the most DC motor. Inside the motor we got resistance and the in series with the inductance. Okay, and then the power energy here is the angular velocity times some constant. Okay, it's the output power. And then we got current flowing through this motor. Of course, you need to apply one voltage. And then, of course, when it comes to this motor, we have one new parameter called the speed, the resolution per minute, speed in resolution per minute. We call it RPM. We're going to introduce with the rotational speed here. Okay. And this is the energy generated by this motor, change of the flux over time, d flux dt, can generate the voltage. If you rotate this motor without the input power, if you rotate this motor, you're going to generate the power, which is a generator. Okay, so basically what we're going to do today is to simulate the electric motors and the generator. You see, we place one motor on the top, one at the bottom here. One is to we supply the power. You see, one we supply the power. The other one we didn't supply any power, because this means these two motors are coupled. When they are coupled, that means this will become a generator. Let me show you what I mean. In the real lab, you have one motor. Let me find one very obvious example. In the lab, we are using really small DC motor actually. So why we are doing this actually? Why we are putting these two motor coupling them together? Is to measure the some parameters of this generator. Sometimes we need to find the RPM, the currents, and the currents, the voltage, so that we can calculate the resistance, the internal resistance of this motor. Let me show you what do I mean. We call this a model. You see, when we come to the AC or DC motor, right? Inside we have this internal resistance. Sometimes we call the inductance. Happen in the core. Sometimes in the coil. Okay, we got all these parameter. It's kind of like a fixed model. This is equivalent to the motor. Also transformer also got their own model. So inside this model, we have all the parameters like R2. Usually is the secondary. We got this inductance, or we call it reactance. This reactance in the secondary. Okay, we have primary and secondary here. So all this value, sometimes when we get the one motor which is with all this unknown value, by doing some tests, we can actually predict all this value inside the motor. That means we kind of like doing a reverse engineering by giving you the motor without all these parameters. Sometimes engineer can do a test to reverse engineer to find what is the resistance inside the motor, so that they can reproduce their own motor, right? They can copy the design, right? They can copy the design if you know what is the resistance inside the motor. That's why sometimes we need to do all these tests, like we power one motor, and then we're using one coupling here to couple to the next motor. Because when this shaft rotating, you will rotate this shaft also. So this behave like the electric motor. This behave like the generator. So they are totally two different things actually. You can imagine something like this. So to put it in a very simple term, let's say you have one motor like this here. Let's say you got one motor here. I think you've seen many motor before, right? DC motor. So this is a shaft, the motor shaft. Okay, let's talk about the DC motor, right? Because in this lab we are using a DC motor. So if you apply some voltage here, actually you are powering up the electric motor. So this is an electric DC motor, right? Electric DC motor, right? When you receive the input power, of course, you are providing some kind of mechanical movement here. So this is the output, right? It's a mechanical, something of mechanical, right? Mechanical kind of action, right? With this, we call the angular velocity. Okay, in RPM, we can convert this to RPM also. And then we also got some torque also. The shaft also can output some torque, right? So basically, this unit here is functioning as the electric motor. Okay, the input here is the electrical power. The output is the mechanical power in speed and torque, right? Input and output. So if we coupling this together, imagine we placing another DC motor here, exactly the same motor property. Okay, we place them side by side here, facing each other, and then in the center here, in the center we put some coupling. So this is called the coupling. So they kind of like, when this rotate, this will also rotate. When this shaft rotating, this shaft will also follow rotating at the same speed. Okay, and by doing this, here we got input power, right? Used to be input power here. Here you can measure the output. You can measure the output current and the voltage generated by this motion here. So this is no longer functioning as the electric motor, but in reverse, this is functioning as the generator. I think you know what's this term called generator means, right? Generator means you provide some mechanical power at this end. At this end, you provide some mechanical power by rotating the shaft. At the other end, you are getting the electrical power as output. So they are actually opposite each other. This one is applying power, you get the mechanical power. This one is the you apply the mechanical power, you're getting the electrical power at the other end. So that's why we are doing this experiment by coupling these two motor together. So by doing this, eventually we can predict all the resistance inside this motor, the reactant inside this motor also, and then the reactant also inside the rotor, the rotor core. We can predict all these parameters inside this by doing the experiment. Usually the experiment involved is something like open circuit testing, and then the other one is the lock rotor testing. By locking this one, and then we measure the input energy, the input current and voltage. We also can predict some other parameters. So this is the purpose why people want to connect the motor together, like what you've seen just now. Why people want to connect these two motors side by side, facing each other? Because they need to do some testing. Okay, they need to find out the performance, the parameters of this unknown motor, right? Sometimes, let's say you are the manufacturer of these electric motors. You are getting the motor from your competitor, and then you want to find out how they design this one, you can do the test like this. And then you can actually extract all the technical parameters value from your competitor's motor. And then you can design your own, probably with better efficiency. Okay, this all the reason behind this lab. All right, guys, let's start the lab now. How many steps we need to do actually? So first step is to register yourself with this online, Multisim Live online. Okay, I think by now you already registered, right? Okay, I got one message, but the message is not appearing. Strange. It's gone now. All right, I think step one you already done, but we still need to put this in, right? Introduction. I'm not going to spend some time here to show you how to write the introduction. You can refer to this introduction here. Try to summarize a bit, okay? Try to summarize a bit. You don't need to be really in detail. Just briefly go through the theory behind this DC motor. Okay, then the next section will be procedure. Procedure step one. Let's cancel the bow. Procedure step one is register yourself with this link. Right here, copy and paste it. Okay. Arrange a bit. Remove this redundant text here. Log on to Multisim website. Okay. Next step is after login, click on the button create circuit. Okay, click on the button. Where is it? Let's go a bit. Here, create circuit here, right? Let's cut and paste this screen. And highlight this one. I think I better do without the just copy the whole thing here. And resize it. And followed by a label it properly. Figure. I think this is a lab 4. Figure 4.1. So create circuit here. Save. Let's follow it step by step. The window for the new circuit will appear after the Okay, let's copy this thing. Now it's 4.2. We have to change this accordingly. Okay, after you click on the web page here, create circuit. What you'll see in this, you'll take a while to load the platform, and then what you can see here is your new window. Is a new window for you to draw your circuit. Okay, let's copy the whole screen here. Okay, and put it inside here. Resize it. Okay, and label it figure 4.2. All right, we are done. Now let's look at the following step. Start placing the component for the circuit. Select DC voltage source as shown. All right. So basically, what we need to do is start placing the component. Set the voltage source to 1 volt. Okay, just do this step. Copy. Step number 4 right now. Selecting the voltage source set to 1 volt. This is very easy, right? It's right here. Can you see which one? This is the one, right? And then you click on this. You select the DC here. Beside is a DC current. This is not the one we want. With the one with the arrow is a current. We want the one looks like battery. So select this one. Place somewhere near here at the top left-hand corner here, and set to 1 volt. Initially it's a 5 volt, right? How to set to 1 volt? You left click on this 5 volt here, and then you come to this 5 volt text here. You left click, double click again. You type 1 enough. 1 means 1 volt. Okay, and this one can reduce it. So this is the first step here. Let's copy this one. Remember, we need to show all the screen capture. Under the step 4. Forget about the label also. Figure 4.3. Can you follow? I'm actually doing this at pretty enormous speed here. I'm not sure whether you can follow or not. One thing I try to emphasize is that for every step you completed, you need to show that as a proof by capture the screen and put it in your report, and then do a proper labeling to show that you actually you are doing this yourself. You are not copying this from website or from others. Okay, make sure you do that. All right, let's see the next step. Next, place the DC motor by selecting the electromechanical machine DC motor. Okay, let's copy the whole text here. I think just nice. So we need to show that we do this step, right? We need to show that. let's go back to the website again. I think it's right here. If you can, you notice the symbol exactly the same. But here you got some selection you need to make, right? So let's go to this machine. We got two here. Machine wound field. This one is the DC machine permanent magnet. So we want to select the one with the permanent magnet inside here. Actually, you need two actually. I press one here. I press another one at the bottom. Here is something you can duplicate or copy. You can click on here to make another copy and place right below the other one. So are you following or what? Okay, let's capture this screen. I think it's not nice to show the untitled circuit, right? Let's name this as lab 4. I think this is lab 4, right? Lab 3, lab 4, lab 5. Yes, this is lab 4. All right. Capture the screen. Just a partial screen will do. Don't forget about the Lego. Now it's 4.4. It's pretty simple right now. No complicated step. I hope you can follow. Don't forget to save your work. Sometimes some old notebook, when the battery is down, the notebook will just shut down by itself. So make sure you save this often. All right. Let me see if got some message coming in. Someone saying some login information. I think the student is in. All right. Let's go to the next step. Place a register. But here we need to change the figure here. 4.6. Connect the component as shown in 4.6. Okay. Let's copy the text first. Then let's copy the text into our report. Remember, we need to do it all at once. So this will be figure 4.5. I'm worried about this, You know, I see one problem. I see one trap actually. Right now we are in figure 4.4, letter 4.5, right? But when you later on when you try to complete your introduction, if you insert any figure, let's say you insert figure 1, then this one cannot call figure 4.1 anymore, right? So can you see the problem here? But I think there's a need for you to rename this number after you insert any more new figure in at this introduction section. Make sure you do that, okay? You cannot say here's 4.1, here's another 4.1. that means it's contradict, it contradict each other. So try to avoid this this kind of mistake, okay. So right now we are starting with 4.1. That means you cannot insert any figure here if you want to do the introduction. Usually introduction you need to insert 1 or 2 figure. That's why later on you may need to change all this again. Okay, change this numbering again. Okay, let's copy this figure 4.6. Copy this to our report. So right now it's called 4.6, but here is 4.4. So for now I just follow the sequence. I just follow the numbering. I know that later on probably you need to change it again. But it won't take too long to change the number. I think just a few minutes will do. Because here refer to 4.5, so I might have to make sure this figure is 4.5. So what we need now is a register here. The resistor here, so that we can measure the currents. You know why we put the 10 ohm here? It's easy to divide. When we have the voltage output here, indicated by this V here, when we can measure the voltage, in order to measure the currents, we need to put one resistor here. So we use a 10 ohm. So what I mean here is we need to insert 10 ohm and one ground at the center here. So here is the center. Center is the ground. Okay, let's do that. Let's go back to here. Let's find the ground. So ground is the first one, easy to locate. Put it right here. Okay, and then we need another resistor, just at the third position here. Put it here, somewhere here. Okay, move this one slightly down a bit. This platform is easy to move the component around. So what left us to do is the wiring. Let's do the wiring. This is a bit tricky. You need to move your mouse around this this region here. When you see the symbol, when you see this symbol, I don't know how looks like a hammer or something. You just click, left click, and then you can join a wire just like this. Click to join. So this forms the current path number 1, the wire number 1. So we go ahead and do the other one. Move your cursor until you see this symbol. Join to the ground. Okay, I think it's pretty simple. So how about the next circuit here? I know here you need one connection. There is a connection between the motor to this resistor. And then for this resistor, the other end of the resistor, you see sometimes the thing just won't appear. And connect to the ground. This point is the ground actually. You can see the ground is here. This point is the ground. And then nothing else but the last wire like this. I think almost done. Almost done. Okay, now what I need to do, let's compare with the lab report. M1, M2, this is wire 2, wire 3. Okay, before we forget, let's change this one to 10 ohm. Okay, and the last thing to do is actually the coupling. This is not a wire. It looks like a wire, but it's actually, this one is a coupling. So this is something that you need to convince yourself. The red color here is a wire. Okay, nothing wrong with this. It's a wire. But this red color line here is not a wire. This functions as a coupling. So you know what coupling means, right? Let me show you. Actually, you can get this one anywhere online, probably Shopee or Lazada. You can get this coupling. You just need to match the diameter of your shaft, matching each other, because sometimes the motor here is small, sometimes the motor shaft here is bigger diameter. So you need a coupling like this. So the coupling usually they look like this, right? With the different, sometimes with a similar shaft diameter, sometimes with a different shaft diameter on each side here. So they come in various form. This is the most common one. The thing right in the center here, the orange color is a rubber actually to absorb the vibration. So these are blue and the orange rubber is to absorb the vibration, and then these two shiny part is the metal. So this is called the coupling. Sometimes the coupling is just a whole metal piece here without any rubber. But when it comes to our simulation here, this wire is a coupling. That means there's no current and voltage on this wire, just to let you know. So after you've done this, let's copy to your lab report. I hope this is correct. This is correct. Place a resistor. Connect the component as shown 4.5. The current and voltage probe can be obtained from the analysis. So we need to insert one voltage here. One voltage here. So this voltage here is in the shaft. Probably you're confused now. You're confused again. Just now I said that the shaft, motor shaft, you cannot get any voltage out of the motor shaft, right? I think logically everyone knows, right? It's impossible to measure the voltage from the coupling. Actually, this one is measuring the speed. Okay, once more, this red line and this voltage here is measuring the resolution. Okay, measuring the shaft, the speed of the shaft, of the rotating shaft. Even though it's using the voltage, later we can change the unit a bit. Okay, we can convert. Later on, we can convert the voltage to angular velocity. We can convert this one to RPM. Later, I'll show you how. Okay, later we can convert this one to RPM. We just need some equation, I think. So I need to insert figure 4.5. 4.5 is the, I think it looks exactly the same, right? Exactly the same. Do we need to actually insert this one or not? Just take it out first, okay? I don't think we need to do it placing exactly the same thing. Okay, let's insert the numbering again. All right, let's go ahead and do that. Currents. Let's insert the currents. Go back here. Current is right here. Very easy, right? Press one current here. Press another current for the generator here. And what else? Oh, this current is pointing this way. Okay, let's follow exactly the same. This current is pointing to the right. Pointing to the right hand side. This current is pointing downwards. And this V as the velocity to measure the speed of the shaft. Voltage and currents. Voltage reference, digital voltage right here. Okay, another voltage is right here at this corner. Anything along these lines will be okay. Anything along this line. Okay, let's do that. Voltage on this line here. So we are almost done. I think we get everything properly set up. Now we can start our simulation pretty soon. Let's see whether this one can save or not. Let's save this one. Save as the DC motor. Let fall. If you don't save it, if a PC shut down, you need to redo again. How come this thing should appear? I already saved the thing. Oh yeah, disappeared. Okay, now I already saved, so the asterisk is gone. Okay, let's see the next step. By running simulation, measure the input currents, output voltage, output currents, and this is the one, the rotational speed of the motors. Plot the graph showing the changes versus the time between the input current, output voltage current for M2. Okay, just do it one at a time. First, copy the text here. Move to step 7. Okay, read one more time carefully. Measure the input current to motor 1, output voltage produced by motor 2. I think they are all in a separate graph. I think we cannot squeeze everything into one graph. They must be all in a separate graph here. Let's do the first one. Measuring the input current to motor 1. Let's measure the the current here. Okay, come to this interaction. Click on the run simulation. All right, so this thing is showing the numbers running. All right. Hold on, let me see something. Okay. Switch this one to grapher. So it show the progressing reading, right? The current keep increasing. Okay, it show all this current. Let's split the screen. Doesn't help. Okay, change this one. We want to look at the currents, the input current. So let's cancel these two. Okay, the time division here. Increase the time division a bit. So this one show the input currents. It's starting at 700 milliampere, and then it's slowly reducing. Currently at okay, here looks like 100. Oh, this is voltage. This is voltage. This is current. So on the left hand side is the voltage starting from 700 something millivolt. It can, but the coordinator here show only the second and the currents. But here is the voltage. Here's the current. So we have up to 5 ampere of current. Let me make sure this is correct. Looks like it's a bit higher. Looks like it's a bit high. Let me see which step is wrong. Let me see. Let me stop the simulation. Let's go back to schematic. $300 volt. No, this is not 300 volt. This is the speed. This is the speed. Let me see. I can change this one to rotational speed. But I cannot modify this thing. Let me see. I can change it to speed. There's nothing I can adjust here to change to speed. Let me double confirm the voltage. Here's 1 volt, 10 ohm. Something about this motor we need to adjust. There are some parameter we need to key in. I'm not sure whether should we follow the default value or not. Let me read again. Oh, here I need to change something here. 5 ohm to, wait a minute. This is step 7, changing the value of the root resistance, the root resistor from 10 ohm to 5 ohm. But initially we need to use a 10 ohm. Now my question is, do we need to change this value or not? Let me compare side by side. 0.2 ohm. It looks like everything the same. 3 milli. There's no instruction saying that we need to change the value of the motor, the property of the motor. So I'm going to leave this one at it is right now. I'm not going to change the motor parameter. Okay, I'm not going to change this motor parameter here. But somehow the value is a bit high, 400 something for the input PR1. PR2. Hold on. Let me see the PR2. Let's run it. Later we need to capture the graph. But the current is just too high. I don't know where I got wrong. Current is just too high. PL2. Here got a maximum and minimum. Let me change this one. Try. So the voltage wait until it stabilizes. You can probe one at a time. I think you should probe one at a time. Now we are plotting the PL2. PL2 is what? PL2 is the output current, 76 milliampere. The current is a bit high actually. But we are using 1 volt, right? 1 volt. Let me double confirm. It's 1 volt. Here's say 1 volt here. Let me confirm before we plotting the graph. I want to make sure is the 1 volt actually is the one we need to put in or not. Resistor, motor, 1 volt. So I'm quite sure it's 1 volt here. I'm quite sure here is 10 ohm. Later we need to change to 5 ohm. So this is the thing we have to follow. Now I need to, let's stop this thing. Now I need to actually confirm how to change this one to the rotational speed. How to change it. Okay, let's go to the Google and help see whether can help us. We can find the solution here or not. Multi-stream, convert voltage to rotational speed. Let's see, is there any equation we need to follow or not? Let's see Is there any equation we need to follow to convert it to a rotational speed? Let me read the some guideline here. I want to make sure the voltage we measure, is it showing the actual speed, or we need to convert it or not? The speed in radian per second. I think that one, the unit is a speed in radian per second. Let me see. Convert radian per second to RPM. So just now the reading is, let's go back to the reading, 295. Let's key in to make sure this makes sense or not. 295 radian per second. RPM is 2000 something. This makes sense actually. I remember in the lab, when we are measuring the actual motor speed, because before the MCO, actually our student actually put together the actual DC motor, not using the simulation. I remember the speed is somewhere near the 3000 RPM, 3000 round per second. So what we are seeing there, what we are seeing on this result here, actually is the angular velocity speed. Okay, we call it a rotational speed. You can also call it angular velocity. So what we are provided is the radian per second. Here is a radian per second. Even though I cannot prove it's a radian per second, but according to the user guide here, the output is in radian per second, not in RPM. Speed in radian per second. Okay, to convert to RPM, you can use any online tools here. What is this? You can use online tools here to convert the radian per second to RPM. Of course, you can also use your own calculation, use your calculator to convert. But here is not the main point. The main point is the RPM is 2000 something. I think what we are getting here is a valid. Okay, so we're going to take down the first graph. We're going to capture the first graph. So what is the first graph? The first one is input current to motor. Here, this current, so-called the PR1. Okay, I'm going to show you how do I capture this. First, you run the simulation, okay, and minimize this thing, and click on the grapher. You see the things start plotting, right? And then it's plotting these 4 parameters. Now we just want to plot only the PR2. You can click here to refer. Sorry, we want to plot PR1 input current to the first motor, to the M1. One more time. Input current, this is power. Input current sent to the motor 1. start plotting not right now, but we just want to show the we are only interested in the only one parameter at a time. So you click on this gear, something looks like gear. Click on this icon, cancel the one you don't need, leave the one you want, PR1. But as long as you do this, the thing disappear. It's because the value is too small. We need to adjust. Okay, adjust something here, the current. Let's see the currents. See, the currents are putting up. You cannot just show you people this the current, right? So the PR1 is a green color, but I didn't see any green color here. I think that the current is too small to be appear on the graph. So I cancel this. Then I cannot see the graph. I think it's too small. Let's change this one to 0.1 and see what happens. 0.1 is still nothing here. Let's see 0.01. Still nothing, right? Is it more than 1? Oh, it's really high. The current is really high. So we need to change it to something more than 5. Let's see, change to 7. So the current is quite high. Ignore the voltage here. Now we are looking at the currents, because this PR1 is a current, even though it says a voltage. Okay, even though it says a V1, but it's a current. It's a negative I. Negative I. You refer to here. The most important thing is that this is a PR1. PR1. This is the A. A is a current. So PR1 is a current. Go back to here again. PR1 is a current, of course, and this V is kind of confusing. Okay, but we only look at the currents. So from the 0, current start from something like 1 volt. Current start from here. Actually I don't know how to move the current to the right hand side, but it's okay. It's okay to show people that the current right now is lower than 200, lower than 1 ampere. So in order to adjust the voltage side, let me see. I can adjust down to 5. See what happens. Now I adjust 0 to 5. It starts from 1.5, and then it gradually reduce to 4, 6. Okay, let's change it. So if you select the wrong time division here, it looks like a flat graph. This is not good, right? This is meaningless. This graph is meaningless. So you need to play with this time division, and make sure you can get a meaningless kind of meaningless something with meaningful. So I now adjust up to 5 seconds per division. One division is 5 seconds. This is one division into the 2 seconds. This is a 5 seconds. I think we can use a 2 seconds will do. 2 seconds per division will do. So it start from 5 ampere, and then it gradually reduce to, you can see the time and the ampere. The value shown on screen is the time and the ampere. Right now it's slowly stabilized at about 300 milliampere. So we're going to wait a bit longer. Wait a bit longer until it stabilize, almost reaching a flat curve. Okay, just be a bit patient. But remember, it start from 5. But right now you see this part disappear already, so you need to change to 5. So it starting from 4.8, starting from 5 ampere actually, 5 ampere. I think it's now come to stabilize already. I think it's now we can capture the graph. So we cannot export it. We can export. Let's see here. Let's try to export it. Export as the image. Export the graph image. Okay, and save. Let me try to save this one. And usually the most important thing is to label it properly. PR1. All right, so it looks like this. Okay, let's capture this one to our report. So so here is where we insert our test result. Input current to M1. Just click this one. Okay, I click multiple times just now. So what you do is you go to your where you keep the file, the result, right here, PR1, just put in. Oh, it's a kind of oversized, reduce it to fit into the document. Then, as you know, we need to do labeling, right? Figure. This is difficult. 4.6. Input current to M1, to motor M1. Okay, we've done the first one. Even though this look really the text looks very tiny. The other thing we can do actually is to capture this one using the tools here. I think this you'll get much better result. Make sure you show the currents and the because we are not looking at this 5 volt is the current actually 5 and 5 about 5 ampere. Okay, let's capture this one properly, including the X and the Y label, currents, and the division, the time scale. Okay, replay this one. I think this one look really ugly. This will be much better, right? Do you think so? The text actually, the text is the easy to read. I think it's better than the previous one. So I will use this one because I find it easier to read. Okay, the next thing to do is capture the output voltage produced by the motor 2, which is output voltage produced by the motor 2. Let's go back to our schematic. Which is it? Output voltage. This is the motor 2. This is the voltage. So this is a PR4. So we go to grapher. We choose PR4. Deselect, unselect the PR1, choose PR4. Okay, and then do some adjustment. Because the voltage 0 to 5 is way too high, let's adjust this one to something like 2 volt and try to see whether it make anything. So it's still too high, it's still too low. Adjust to 1.5. I think we better stick with 1. So this one show the voltage from 0 all the way, the generator voltage from 0 now stabilize at about 900 something millivolt. Okay, let's capture this thing because it looks almost stabilized now. Now we don't need the currents, we just need to show the voltage. I hope you can see the point. We only show the voltage, don't show the currents, because output voltage is about the voltage, not about the current. Okay, press it inside your report. Resize it. Now should be figure 4.7. This is called the output voltage of M2, of motor M2. So there are a few more. Output voltage provided by the M2, we did just that. Output current produced by motor 2. Output current. Where is it? Output current. Here. The name is called PR2. Okay, go to grapher. Don't need to stop. Okay, go to grapher. Change this one to PR2. Here, show PR2 only. This is the output current. Later we need to capture the current. You cannot just show this to people, right? This is not properly presented, right? It's not properly presented. The scale is out of scale. So we need to adjust it. So the current is about 92 milliampere only. So let's change the current to 0.1 only. 0.1 means 100 milliampere. Enter. So it looks much better. Okay, so now we can capture the this graph from this corner here. From this corner, show the current. I want to show the text current. I don't want to show the voltage, so I stop here. So show the current at about 92 milliampere. This is the time scale. Every division here is a 5 second, 5 second, 5 second, 5 second. So it takes about 15 seconds to reach the to be stabilized. Okay, about 15 seconds. So let's put this one, insert this one into our report. And this is called figure 4.8. This is called output current of motor M2. I think you can follow. Now what we left is a speed. The last one is the speed. So here's repeat again. You say plot the graph showing the changes versus time between input current M2, output voltage, output current, and the speed. So as you know, we need to show this one individually. We cannot mix these four into one graph. It's hard to adjust. It's very hard to adjust the scale. So the last one is the rotational speed. Let's go back to schematic again. Let's confirm the speed is PR3. I hope you can see PR3. Probably you appear different on your PC. Go to Grapher, select PR3 only. You can see my PC starts slowing down. I think the data is getting larger. That's why the PC starts slowing down. Unselect PR2. Select only the PR3. Okay, so you see, you cannot just present this one to a user, right? There's a meaningless. So I remember the PR3 is 290 something in voltage. So I need to come back here to change to something about 400. Let's start with 400. By showing the 400, is a 300 something. The speed starts from here. This is a 0 second. So let's start with 350. I think this is good enough. Okay, I think this is good enough. Because all the while we start from 0. So if we change it to 10 seconds, we change to 10 seconds, we can see it start from here. We can see actually it start from static. You start from 0 speed, and then it increase rapidly to 312. But be careful, now it's not the volts, now it's the angular velocity. But what we can do is, I will capture this this graph. I will just show the voltage here. Okay, this is the one I want to show, the speed of M2. Okay, come back here. Remember, you need to tell the user that this figure is not the voltage. 4.9 is actually the motor speed in radian per second for motor M2. It's not in volt. It's a bit confusing. Actually, in the real report, you need to change this one to angular velocity, radian per second, because by showing the voltage is a misleading actually. People think that this is a generator output voltage. Actually, this is not the output voltage. It's a motor speed in radian per second. Okay, you can convert this one. Just I show you, you can convert this one to RPN. You can discuss this one in your conclusion or discussion. Okay, you can say that 295 radian per second actually is 2008 RPN. You can talk about this one later on. I think we are done now. We are done. But we need to repeat everything again with 5 ohm and 1 ohm. Repeat everything again with 5 ohm and 1 ohm. Initially it's a 10 ohm. So initially it's a 10 ohm. Right here. Now we need to do it in 5 ohm and later on 1 ohm. So this one could take forever. It's better for us to put in this one is a 10 ohm. This graph is for 10 ohm. Okay, copy this one to the end of the label here. All this is 10 ohm. So the first step number 8, repeat everything, repeat only the step 7, change it to 5 ohm. So I'm going to leave it to you. I think you know how to do, right? First, what you do is you come to schematic. I'm not sure whether you need to restart the simulation or not. Looks like you need to restart the simulation. So you change this one to 5 ohm. Make sure you done the previous graphing. You change to 5 ohm. I think you need to restart the simulation. I don't think that the simulator can produce the output without restarting. The C is getting very slow right now, and it's still using the previous parameters to generate the output. I think and we need to stop now. Stop the timing. Stop the simulation by pressing this button here. Go to schematic again. Make sure it's a 5 ohm. And run again. Run the simulation again. Because we are changing the parameter now. We need to restart everything. Now you need to redo everything again. Okay, go to grapher. Let's start with the first one. Input current to M1. PR1. PR1. Cancel this 3. Actually, you need to do this 4 actually. It's not showing, right? Because PR1, the value is 2 point something ampere. So you need to come here to change to 3 ampere. Okay, but it shows only partially. I cannot see the top here. So you need to adjust the time scale. I think it starts from way above 3. Change to 5 and see what happens. Still cannot see the head. Change to 7. Reduce this one to change to 2 seconds, 5 seconds. So it starts from around 5 ampere. And now on the way to stabilize the currents. We have to wait for the current to be to be stabilized. You see, if you compare 2 seconds, you compare 5 seconds, you compare 10 seconds, you can see it's not reaching the stabilize yet. So we need to give some time. It's going to take a while, probably 1 minute or something. Because the time is up right now, I'm going to leave it to you later on when you are free. You can let the PC run for a few minutes, and then you don't need to click the stop. I think you can click the stop later on, and then you plot graph one by one. Okay, plot the graph. These 4 graphs here. You plot it. You put a graph for each one, and then you need to adjust properly the scale here. Okay, and then you need to do the 1 ohm also. The last step is a 1 ohm. Step number 9 is 1 ohm. Remember, you need to insert the graph here. Let me do it. I'm not going to press the stop button. I know this is not reaching the end yet. We still have to wait, but we run out of time. It's impossible for us to plot all the graph right now. So what I'm going to do is I'm going to capture the graph, what it is right now, showing the currents. Okay, then I import it to my step number 8 here. I adjust it, and I label it as figure 4.10. This is the input current to motor M1 for the 5 ohm. Remember, it's a 5 ohm. Previously, the 4 graphs that we done is a 10 ohm. So you can compare this start from about 5, about 3, about 5 here, 5. Actually, it didn't change much. It didn't change much. But this incomplete, right? You know it's incomplete because we don't have time to wait for it to stabilize. It's still running. You can see that right now at 17 seconds, it's still running, but it's not yet stabilized. So this is considered incomplete. Okay, but I just want to show you the 4 graphs here are for 10 ohm, 10, and the last one is speed 10. Now it's a 5. So you need to do 3 more here, and then step 9, change to 1 ohm. Capture the 4 graphs also. So step 10, analyze the result of 10 and write a detailed discussion. So we don't need to write about this, okay? So this will be our last step. After this, after the step 9 will be our discussion. We need to put it as a step, okay? And then the conclusion. I think there's no question here. There's no question for this lab 4. Okay, I leave it to you to write your conclusion and discussion. What I want to see actually is the how you compare 10 ohm, 5 ohm, and 1 ohm. Are there any trend or not? When we change the resistor from 10 ohm to 5 ohm, what is the observation you can get from the graph? Anything so obvious you can see or not after you change the resistance? So the resistance is actually this resistance actually tied to the output. So what I can tell you is you change the output, you change the resistor at the output here, I mean the M2, most likely only these two will change. This one has nothing to do with the resistor here. This one just you provide the power, it's just spinning. Okay, this thing just spinning, and then this shaft of power, this motor 2, and these two values will change because you change the resistance here. So just now we plot the first one, we didn't see any obvious changing, right? That's the reason why. Just now we plot the 5 ohm. So if you compare this 5 ohm with the 10 ohm, almost the same actually. You see the button at the bottom here is about look at the current here, about 500 milliampere. If you look at here, it's also about 500 milliampere. So I didn't see any obvious changing. I didn't see any obvious change between these two 5 ohm and 10 ohm when it comes to the input currents. But I'm quite sure for the output voltage and the output current, also the speed also will change. But the speed changed a bit only. You see the speed, just now I remember the speed is 290 something. Now the speed is 300 something. Whether the speed is increasing or decreasing, probably you can make some conclusion. When you reduce the resistance, the load, this is actually the load, because this is generating the power. This power is to consume by this load. Okay, like you know the reason why we use a generator is to generate the electric power to power some load, right? So this is our load. When the load getting lower, I think the speed should be higher, right? In theory, in logic, when you think about logically, you think about this logically. If your load is decreasing, less load, I think that the generator will spin faster because the load is lighter, right? When the load is lighter, I think we can presume that the speed of the motor, because they're coupling, right? So the speed is the same. We presume that the speed will be higher because the load is lesser. This is based on logic analysis, okay? You can also try to use any kind of analysis, try to draw some conclusion after you compare with three different load, 10 ohm, 5 ohm, and 1 ohm. Okay, so I'm going to leave it to you to complete the rest of the graph. What you need to do is actually you don't need to restart again. Okay, you don't need to restart again. You just need to select the one you want to plot. Example, you select PL2. Okay, the data is there. You just need to adjust it. PL2 is about the currents. Now the current is just too high here, so I reduce to 0.2. So you plot the graph just nice. Okay, so after you wait for it to stabilize, you just change this the setting here, and pretty fast you can just copy the graph. Okay, you can get the graph in no time. The only time you're wasted is waiting for this one to be stabilized. After it's stabilized, you can change any one of this and capture the foregraphs. Okay, when it's stabilized, you don't need to repeat again. Okay, you repeat again only for the resistance value, different resistance value. You can capture these foregraphs once it's stabilized. All right, I'm going to stop here for a while as our second break time. Okay, I'm going to stop the recorder now so that it won't get too long.